I will talk today about a problem that we have in psychology and all ways where we try to understand how people make decisions and should make decisions. Here is the problem. The classical decision theory, such as Savage's, has no normative force outside of small worlds. And let me explain what that means. So classical decision theory can be seen as consisting of three parts, so-called choice axioms that are sufficient and necessary for the maximization of expected utility theory, and probabilities that are updated in a Bayesian way. That's the key idea. And Savage, in his 1954 book, was very clear that the theory has its limits. And he gave two examples. One was playing chess, and the other one was planning a picnic. And he said very clear that decision theory, defined in this way, does not apply to problems like that. He didn't use general terms. I used the term intractability for problems like chess. And I will give you an example in a second. Briefly, intractability means that the optimal solution cannot be computed by any mind or machine. So we need something non-optimal. The optimal solution cannot even be computed if there one exists, as in chess. So that's basically intractability. Machine learning. Every student in machine learning is brought up with facing intractability. And there's an entire terminology about this, like NP-hard, which I'm not going into it. And then the solutions are to this intractability sought, and that's basically what much of machine learning is about. And by the way, I'm here, I try to interest you to think more broadly, more interdisciplinary than some philosophers do. But also some economists or some psychologists. Progress is not in making a career within a small subdiscipline and solving problems that the subdiscipline invented. Progress of science is in getting ideas together and dare and look broadly and envision. So back to the problem. Savage was very clear about the limits, not so much his followers. And decision theory is sometimes presented as if it would be a theory for everything. In Savage's own insight, it's not. And intractability is one of the limits. Uncertainty is a second of the limits. What do I mean with uncertainty? Uncertainty, I distinguish uncertainty from risk. Risk is a situation where you know all the alternatives, all the consequences, and all the probabilities. So if you go in the casino and play roulette this evening, you are in a situation of risk. There's no uncertainty. Uncertainty is much broader. It can involve that you do not know the probabilities. That's often called ambiguity, as in Ellsberg's paradigm. But more deeper uncertainty is that you do not know the consequences. So what would happen if your own referendum about independence would go through? Nobody knows exactly what's coming. That's uncertainty. What will happen in Germany now with the elections and refugee problems? So we typically live in a world of uncertainty where we don't even know the alternatives or their consequences, or we can not even construct a subjective probability distribution about them. The problem is we need to take uncertainty seriously and model it. So the first point is that in Savage's own world, decision theory is about a small world. A small world is defined in Savage's terms as an exhaustive and mutually exclusive set of future situations of the world, so states of the world, and an equally exhaustive and mutually exclusive set of consequences in that world. You need to know all of that to do Bayesian decision theory. That's often forgotten. So a small world is consists of this class of future states and the class of consequences, and it needs to be exhaustive. So, as you know, but philosophers are not so much interested in the descriptive part, it's well known that also the entire set of choice axiom, maximization, expected utility, Bayesian updating, there is clear evidence that people in many situations do not follow that. But I will not be going into in the descriptive time. Let's stick to the normative. So, what happens if one's own choices are incoherent? So, violate any of the choice axioms or the rules of probability. Usually, it is assumed that some violation of incoherence is some not only irrational, a sign of irrationality, but it has detrimental consequences. Does it really? We have done a survey of the entire literature, and we'll go into this. The answer is, we have not found any consistent evidence that violations of coherence are costly in terms of real-world consequences, such as lower earning, less health, less happiness, or even inaccurate beliefs. What is the consequence of all of that? I think we need to develop an alternative theory of decision-making that has normative force outside of small worlds. And by the way, also much of what's not only happening in economics and decision theory, but also in philosophy, is very similar to small worlds, where everything is certain, no uncertainty, no intractability. The emergent, what I will talk about, is one solution out of this problem. That's the creating a science of decision-making under intractability and uncertainty. So, and the tool is the science of heuristics. And that has three goals. It's a descriptive goal to model how actual institutions, how actual people make decisions. Second, a normative goal to model how people should make decisions when optimization is out of reach. So when you cannot say, this is the best way to do. And so, but you can still decide that given some criterion, you can do better than what exists. And it also has applications that we do in intuitive design. So on Monday, I will be at the European Central Bank talking about how to design the present system of value at risk-based banking, which borders on astrology, replace it by something simple and simple heuristics that are actually robust. So the typical models of finance are in the world of risk, but the world of finance is uncertainty, not risk. And the mismatch is there. And they need to dare to develop a systematic understanding of how to make reasonable decisions in a world of uncertainty. So that's probably not your field, but just to illustrate, a large bank today, in order to compute its capital requirements, has to estimate thousands of risk parameters. They are correlated, so they have to estimate a correlation matrix in the order of millions. with limited data, good luck. That's all guesswork. And this is what I mean. It borders on astrology, and the banks can use their internal models. That doesn't create any safety. And here are lots of brilliant minds and large IQ points. And I just challenge you to do something that is relevant for the world. And we can do this from decision theory out. So what I'm doing now in the rest of this talk, I give you examples that illustrate general points. That's basically what I can do. And first, what is intractability? The example is here. Assume you're the president, or you want to become the president of the United States, and you do a presidential tour for the campaign, and you want to visit the 50 largest cities in the United States. Here they are. And you tell your campaign advisor, find me the shortest route, so that I start in a city and also come back at the same city. So that looks simple, but the problem is intractable. There are about 3 times 10 to the 62 routes. That is more than the estimated number of atoms in the universe, just to illustrate that. So that's a kind of intractable problem. In machine learning, the consensus is that most interesting problems are intractable. And if you leave a small world and go in the real world, which is well-defined, so well-defined problem, you need well-defined problems to decide whether they're intractable or tractable, that also holds. How do real people deal with such problems? One solution is they use heuristics, and I just show you here a very simple one. It's called the nearest neighbor heuristic. Start in your hometown, move to the next nearest city, and just do this until you're finished. And that gives you a solution. And then you can study now the ecological rationality of this heuristic, and now do some formalism and find out in what situation is that good. And better than something more complicated. So, intractability. This is an instance of the so-called traveling salesman problem, and the machine learning, the estimation is that the majority of the traveling sales problems is intractable. So you need to recur to heuristic solutions. There's nothing else. And what is uncertainty? I show you the simplest version of uncertainty. So in general, uncertainty it's often confused with risk. Although in the economic literature, Frank Knight has long time ago made a decision, and others have, Keynes for instance, but the uncertainty means, risk means, I repeat, you know all the alternatives, all the consequences, and all the probabilities. Everything else is a form of uncertainty. And I show you the weakest form of uncertainty, where you have a stable population, and you just draw random samples from it, and then make an inference to the population. This is plain statistics, inferential statistics. And even in such a situation, something very interesting happens. What I've shown here are an average across 20 studies that have looked how well certain methods predict from the sample, random sample being drawn to the population. And there are 3 candidates. One is multiple regression. That's the method that most economists use and almost everyone else. It's basically a linear equation where you estimate the so-called optimal beta weights from your sample. And the other 2 are heuristics. I will go deeper into one to take the best. Tallying is easy to explain. You do not estimate the beta weights. You just give every predictor or Q the same weight. Now, that may look something, and it has been traditionally attributed to people's limited cognitive abilities, but you will see with this demonstration that you're just wrong about it. And take the best is another heuristic that has a different spirit. It just takes the best predictor and ignores all the rest. Both heuristics commit sins against so-called rationality. And what you see here in what's called fitting here is, this is not a situation of uncertainty. Here you know all the data about the population. There's no uncertainty involved. And of course, in such a situation, the multiple regression that takes all information in has a higher accuracy, but the two heuristics come close. Now look at the situation of prediction, and everything changes. So prediction is also called out-of-sample prediction here. And the moment, and this is here cross-validation, you do prediction, introduce uncertainty, on average across 20 different studies, the two heuristics predict more accurately than the linear multiple regression. This, the results on tallying have been shown long time ago by a person who is sitting here, Robin Hogarth, and Robin Dawes, who is no longer with us. They have been ignored till the present day. That simpler can be better is not conceivable for many, despite the evidence. And this is just one piece here. It is also important for some philosophical doctrines. For instance, the principle of total evidence by Carnap suggests that you shouldn't leave information at the table even if it doesn't cost you anything. This is true for a situation that's called here fitting, where no uncertainty is involved. It is no longer true for a situation where some uncertainty is involved. If uncertainty is involved, then, as shown here, it is normative to ignore part of the information in order to make better predictions. And this is where the normativity comes in. And I will go in a minute and explain more how we can then distinguish the situations where less is more and where it's not more. So the general point I want to make is that outside of a small world where everything is known for certain, the typical conclusions about use all the information, optimize, do no longer hold. And I'll show you now, in much of the psychological literature, say on heuristics and biases, these two heuristics, using them would be considered as irrational. And the problem is that the heuristics and bias literature does not really distinguish between risk and uncertainty. If that would be somehow irrational, one would find violations of coherence to have material consequences. So violations of here tallying does not try to estimate weights or take the best, ignores independence when ranking, ignores dependence between cues when ranking the cues. I will show you this in a minute. And so they just bet on independence and do better, although independence does not hold. So, do violations of incoherence have any consequences? This is an article which I just show you. You can look into detail. We have looked whether any of these known violations, here are some of them, violations of modus tollens, modus ponens, syllogism, class inclusion, transitivity, Bayes rule, property alpha, statistics, and so on, whether they have been shown to have any consequences of lesser health, lesser wealth, lesser accuracy, whatever costs? The answer is we have found little to no evidence, and certainly no consistent evidence, that incoherence of that kind would hurt. That just fits with the argument before that choice axioms, expected utility maximization, Bayesian updating have no normative force outside small worlds. So, what I will do now in this second part is to give you a brief introduction in the study of heuristic decision making, that is, how to develop a theory of decision making that can deal with situations of intractability or uncertainty. And my own research started where Herbert Simon left us, and we are making three important choices here. First, risk is not the same as uncertainty. In the decision-making literature in economics, you will see that the terms are confused. So what's optimal in risk is not optimal under uncertainty. What's normative under risk is not normative under uncertainty. And also people use different strategies. And you just have seen one example. Second, I believe that we can learn from how people make decisions. We can learn from that to develop a theory how they ought make decisions. That's often called a fallacy. My experience is that there's more wisdom in people's decision making than decision makers believe. And there is no point to, so it's a different starting point. The starting point of classical decision making goes back in the mid-17th century, in lotteries, the origin of probability theory. And these lotteries, where everything is known for certain, are still the typical examples in much of decision theory. What we need is, second, models about how people make decisions as opposed to so-called as-if models. So as-if models are models that do not aim at modeling the process, only the result. And finally, so typically, expected utility theory, prospect theory are to a large extent as-if models, because nobody would believe that these complicated processes are actually computed in the brain. And also, one of the wisdoms that one takes from actually observing people how they make decisions and experts how they make decisions into the models is that real decisions are most of the time much simpler than what decision theorists develop in their complex models. And finally, the key normative point is not being internally consistent. That's what Savage's axioms are about. Transitive. The key normative point in a real world where you cannot check consistency because of intractability is ecological rationality. That is, the success, as you saw in the example about uncertainty before, the accuracy that you generate with something simple or complex. Here's the research program. There are three questions. The first is, what's in the adaptive toolbox of people or institutions? That's the descriptive question. I will not talk about that today, but we have plenty evidence that people rely on heuristics, and also evidence that experts look for fewer pieces of information than novices and rely on simpler principles to integrate them than novices. Ecological rationality is the normative study. That's the new contribution in our research program that was unthinkable before. Say in the heuristics and biases program, per definition, every heuristic is second best and it always should follow the laws of logic or probability. and because of the lack of distinction between risk and uncertainty. Here the question is, can we identify environmental structures or tasks in which a simple heuristic can outperform a more complex model, or vice versa? And intuitive design is the engineering part. I will also not talk about that today. So, why do people use heuristics? The typical explanation is the so-called accuracy-effort trade-off. So you can find that in the classical work by Payne, Bettman, and Johnson. They have formal models, or by Kahneman in his book Thinking Fast and Slow. He has no formal models, just words for heuristics. And the idea is a heuristic is simple, so you have less effort, and therefore you pay, on the other side, a price with less accuracy. That's the trade-off between accuracy and effort. And that is sometimes assumed as a general principle of decision-making. And I just wrote it down in a classical way. The total error you make in decision-making, according to this view, is your bias and some kind of noise. What is bias? So if the true state of the world is a polynomial and you have a linear regression to model it, you have a bias. That's the systematic deviation between the true state and your model. And noise is some irreducible measurement error. This conception is correct in a world without uncertainty. It is incorrect in a world of uncertainty. In a world of uncertainty, the situation is different. The trade-off is not between accuracy and effort, and you have just seen an example where a simple heuristic with less effort can be more accurate than a regression in this case. Yeah? So the accuracy-effort trade-off is incorrect. The trade-off is somewhere else, between bias and variance. What's that? So under uncertainty, the total error consists of bias, as we just had it, but another component that's called variance. I'll explain what that means. So that part is well known in machine learning. Every student is brought up with it. In economics, it's basically unknown. And in most of psychology too. I don't know how it's in philosophy. You know better. And that just signifies how isolated the disciplines are who study similar things. And that's the big advantage of being a director at the Max Planck Institute. I can have in my research group people from all of these disciplines working together. And that's basically the key to the success we have had. So let me explain that, what error, bias, and variance means. Here are two dartboards. On the left side, so the red point is the bullseye, that's you aim for, and each cross is a dart. The player on the left side has a systematic bias, which is defined as the difference between the bullseye and the mean of the darts. So the bias is left, right and down. But it has a low variance. The variance is defined at the squared deviation of the individual darts from their own mean. See that? On the right side, this player throws all along the board but has no bias. So the mean dart is exactly on the bullseye. There is none, but has no bias but large variance. See, that's the image. So the task about good decision making under uncertainty is not to reduce your bias to zero, but to have a good balance between bias and variance. That's the task, which also means in order to get that you have to keep a systematic bias because you don't want to end up on the right side. And And keeping a systematic bias can be done by very many different things. For instance, ignoring weights, so not trying to estimate weights, as in tallying, or just going with one good reason, as in take the best, or other ways. So by simplifying, and simplifying is not due simply to cognitive deficits, as some psychologists believe, but it has a rational reason in order to perform better. So that's the illustration of bias and variance. I give you now one example just to get the idea in your brains. So that's a picture of the temperature, the average daily temperature in London in the year 2000. Every point is one of 365 points. Assume that's all you know. You want to model the temperature curve in London, and you think about polynomials. And here are two polynomials, a degree 3 and a degree 12. So a degree 1 polynomial would be a straight line. Degree 2 is a parabola, and so on. And with each degree, you can have another turning point. Which of the two polynomials, degree 3 or 12, fits the data better? What do you think? The simpler or the complex one? The complex one, correct, yeah? So it's the red curve who does better. That's the better fit. In general, the more complex you have, complex polynomial you have, the better the fit. You see that? This is a situation, there's no uncertainty. You know all the data. That's data fitting. So, and in general, what you see here, there's the error, and lower is better, and a degree 1 polynomial has the highest error, and it goes down and down and down. Yeah? And if you have a degree 364 polynomial, you have no error anymore. You have perfect. But you can see that that's useless. Fitting, or assuming you know everything. Yeah? Question is, if you take all these polynomials that are fitted on the data and make predictions for next year's, which one is the best one? Or alternatively, if it's out of sample prediction, you take a sample and fit your polynomials and predict for the entire space. It doesn't matter, it's basically the same result. What do you think? Where does this curve go? Okay. Is that a pointer? Good. So, two questions. Now, the prediction curve. So you have you've seen two of these polynomials. You use each of them and predict next year's, or you sample them on, you fit them on a sample, predict the year's performance. That doesn't matter. So, will the prediction curve be above the fitting curve or below? Will it have more error or less error? The prediction curve above, yeah, right. Prediction is more difficult. And for those of you who are socially intelligent, you've seen I left more space up there. But the important question is now, what's the shape? And this is not just this example, this is a general understanding about the bias-variance trade-off. What is the shape? Will it go down like that here? That means more complex, better. You made this movement, yeah? U, right. Yeah? And it's U-shaped. And why is it U-shaped? You have here a situation with high bias. So a polynomial of first degree is not a good model of temperature. It's a line. But it has low variance. You just need to estimate two parameters. A polynomial of 12th degree that you have seen has low bias but high variance. If you sum it, then the complex model that did so impressive predicts less well than the totally wrong model, but try to avoid estimation error. So that's the trade-off between bias and variance. And the models with the lowest error are about 3 or 4 polynomial, which makes sense. So this is an illustration of the general principle. So, and it's a normative principle. If we want to make good decisions under uncertainty, and that's what most of our problems are about, then we need to introduce sufficiently bias in order to reduce estimation error. The trade-off is not between effort and accuracy. So, and in the rest of my talk, I will go into into a specific example about lexicographic heuristics and illustrate basically what I've said. Many decision theorists have the misconceptions about heuristics. Here is a quote from Keeney and Reifer's famous book. They say, lexicographic heuristics are more widely adopted in practice than it deserves to be. It is well known that people use them. Yeah. Although after we have demonstrated that they can be better than so-called optimal, others started to doubt that anyone ever uses lexicography, because it cannot be true that what people do could actually be better. But there's no sufficient experimental work to show that people in situations where a lexicographic model is ecologically rational tend to use it. And it's naively simple and will rarely pass a test of reasonableness. You will find no test of reasonableness in their book. We have done them, and you remember the figure I showed you at the beginning with take the best, which is a lexicographic, doing better than linear regression is just an example about a test of reasonableness. What are lexicographic heuristics? Here are 3 examples. Take the best, elimination by aspect, and fast and frugal trees. I will only talk about take the best today. And this is the definition of this heuristic. It just orders cues by the validity, and validity is unconditional. It is, there are no beta weights. It's just an assumption of independence, which is deliberately wrong in order to avoid estimation error for the covariance matrix. And then it stops search the moment the first cue allows a difference. So the typical situation is you have 2 options, you want to find the better one, and for that is take the best. And take the best then just goes with a single cue. And I'm not going in details here. Important is that the validity is a simple form of correlation between each of the predictors and the criterion, and there's no covariance matrix or conditional probabilities being estimated. Why? In order to reduce variance, a bias is increased. That's the logic. And so take the best is, so Thomas Sturm and I have written a paper on naturalizing rationality, and it's a good example that you take something which people use and investigate it. To what degree can it be a good normative model? Take the best is used everywhere. Traffic rules. Which car has the right of way? There are 2 cars on an intersection, and it's lexicographic. If there is a police officer, that's it. If there's none of them, it's the traffic light, that's it. If it's not, there's no traffic light, it's the sign, and so it goes down. There's no attempt to weigh and add everything. That would be the end of safety. Just think about a moment of that. All theories of rationality in the traditional science do all weighing and adding, Bayesian or whatever. And lexicographic strategies that provide actual safety in the world are called as You've seen the Reifer and Kine quote, as something irrational. So another example about the real world. Now, FIFA rules. So if you have a world championship and there's a group and the decision is which of these 4 or 5, which 2 will go on, there's no weighting or adding. It's another lexicographic rule, the total points. And if they are equal, then you go down. The points in the direct competition matches. If they are equal, you go down. It's all lexicographic. Or one of the greatest inventions in civilization is the so-called Arabic number system, which is lexicographic. And it has a huge advantage over the Roman system. Which number is larger? Very difficult to say from the Roman. But if you write it in this Arabic, which is actually Indian system, then you just start left. 1 and 1 are equal. That's the first cue. Go on to the next one. 9 and 8 are different. That's it. So that's the same spirit. Now, so that's the way we proceed. We just look in the world and see intelligent systems and analyze them. What I'm now doing with you is, we'll do this fast, just to get an idea. How can we study the ecological rationality of a heuristic like take the best? So you start with the total error bias with bias variance dilemma, and we know the components of variance. That's plain statistical theory. I'm not going into this. The more parameters you have, the higher the variance will be. The smaller the sample size, the higher the variance will be. And so take the best is clearly of an advantage on the variance side compared to standard models like regression. But what's about the bias? And that we haven't understood for many years, but now, with the help of quite a number of researchers, we can now exactly say under what situation will, relying on a single reason, as in take the best, give you exactly the same accuracy as any linear model. And note, the bias component corresponds to the fitting situation. There's no estimation there. And the variance component brings the advantage. And we have here a situation, if one of these 3 conditions hold, which I will explain in the situation, then the bias of take the best is exactly the same as any linear model with all of its estimations. And so you get the same result in fitting, but in prediction you have an advantage by reducing the estimation error from variance, and that explains why relying on a single reason and leaving all the other information away gives you a higher accuracy. So this is a situation where the principle of total evidence does not hold. And what are these situations? So let me repeat. If one of the 3 exists, then there's no linear model that can ever beat take the best, and in prediction, take the best will do most likely better because it has less variance. Dominance is easy. Assume you choose between A and B, and you have 3 predictors or Qs, and they are represented here by gold, silver, and bronze medals. And in this situation, A dominates B. You can see A. So because on the left side, there are always as many coins on the right side, and in at least one case it's more. That's easy to see. If you have a choice between 2 and all aspects here are at least as good, but and one better, it dominates the other one. And in domination, you don't need any sophisticated model. Just forget it. More interesting is cumulative dominance. And this is, here you change now the definition of what a variable is. It's no longer gold, silver, and coin, but The first variable is gold. The second variable is gold plus silver. And the third, gold plus silver plus bronze. That's what cumulative means. So on the first variable, gold dominates, A dominates B. B is on the right side. And then you have, although the silver do not simply dominate the other ones, but cumulatively they are the same, and the same holds for the third one. One can prove that if there's cumulative dominance, no linear model can ever dominate a simple lexicographic take the best. And finally, non-compensatoriness, the third condition, is also intuitively easy to understand. Here are 5 Qs or 5 predictors. If their weights are exponentially decreasing like that, like 1, a half, a quarter, and so on, then one can see that no linear model with the same order of Qs can ever lead to a different decision than take the best. So now the big question is, now we know this, we can now explain these strangely looking results that simple can be better than more complex. The question is, but how often do these situations occur in the real world? If there's almost never a situation like that, then it's a very nice result, but it just is also a result for a small world inside the world of uncertainty. This question is hard to answer because we do not have a set of all problems where you could see. The best that has been done is to look at the typical machine learning data sets which are from everywhere with any kind of precision. And here is a study in 51 of these data sets from the all real world data sets from many things. If the variables, so the predictors are continuous, then in 90% of all data choices, and if they are binary, then in 97% of all individual choices, you find these structures. So let me come to a conclusion. So my question in the second part is, the provocative question is why biased minds can make better decisions. And the key to understand is the bias variance dilemma. And here are some ways to introduce bias into your judgment in order to make better decisions. One is equal weights. I mentioned this in the context of tallying. The second one is one reason heuristics. I've talked about that. Sorry, that would be a special case of a lexicographic heuristic which just has one reason, and finally lexicographic heuristics. So here's the summary. Present-day decision theory, which is defined as by axiomatic rules, expected utility maximization, and Bayesian updating, has its role, but its role is very much limited. Its role as a normative theory is very much limited to what Savage called small worlds, and there are not many examples. Most of the problems we deal with are either intractable or uncertain, and we need to develop a systematic way of decision making that we can understand how people make decisions in these situations and also how they should make decisions in these situations. The answers to the normative question, how they should make decisions, are strikingly different from the answers we get on the normative questions within a small world. And you've seen a few examples. In a small world, there are no less is more effect. Carnot's principle holds, but in a world of uncertainty, these results do no longer hold. And we need to study systematically how to make a normative decision. That's the study of the ecological rationality. On the methodology, which I haven't talked very much, we need formal models of heuristics, otherwise you cannot prove anything. We need competitive testing. You've seen that between a heuristic and a so-called optimization model. And we need tests about predictions, such as out-of-sample predictions. So this is what I wanted to bring to you, and I hope that I may have caught the curiosity of one or two of you who dare to think out of the box. Thank you for your attention.
Thanks very much. Questions?
Thanks, that was really interesting. This is just a general background question about the program. How tight are you assuming the relationship is between being rational, or the rational strategy, and the optimal strategy in terms of getting the best outcomes or certain desirable outcomes? Because it seems like you're assuming these things are very close together. There are these phenomena that might give one pause, right? So Thomas Schelling, years ago, the economist, had these famous cases where, at least he described them as nations, individuals can actually do better in kind of foreseeable and predictable ways by being irrational, right? So maybe the country that's known to be irrational doesn't get threatened as often because the would-be threateners can't manipulate the behavior and so on. And in philosophy, famously, Newcomb's problem, right, between one-boxers and two-boxers, where it's generally agreed that the strategy of one-boxing will yield more money over time. Nevertheless, at least the two-boxers aren't willing to concede that we can infer from that one-boxing is the rational strategy. So still say two-boxing is. So just wondering, sometimes it looked like the argument was, well, this rule, there's no evidence in the literature that people who follow this rule do better with respect to these dimensions. So it just raised for me the question of how tight you're assuming the connection is between rational strategy and getting the best results. Thanks.
Okay, first, under uncertainty or intractability, you will not ever know what the best result is. So you can't optimize, by definition. So any talk about optimization makes no sense, is irrational, if you want to. But you can make argument which does better on a criterion than something else. That's what all the ecological rationality is about. We need to make that first step. We need to realize that we create illusions of certainty by constantly talking about optimization. In a small world, you can do it, but not outside. Second, the rationality and what is the meaning? I assume your question was, what is the meaning of rationality under uncertainty? It's no longer optimization. It's not a maximization of expected utility. It is a rationality that is functional, that has little to do with consistency, that is about being more accurate, but about achieving a goal, about getting people what the goals can be, more healthy, more wealthy, whatever it is. But it shows you that important insights that under uncertainty and intractability, you probably do better, and you can analyze that in detail, by systematic studying what experienced people do. And take it seriously, and you will find that less is often more. And heuristics are not second best, but actually can do better than optimal.
Just quick, here's a better way of asking my question, I think, than I did the first time. Can it turn out, the way you're thinking about rationality, that empirically we learn that rational people do less well than people who aren't rational?
Now, if you now mean with rational the old-fashioned way, so Bayesian updaters, for instance, I do not know. So the studies I've shown, the Arcus et al. Paper in Decision, we have found no evidence that those who are irrational by the classical standards would incur any costs in health, wealth, or happiness, or anything like that. On the other side, those who try to be rational by the classical standards, there are a few studies which have compared the accuracy of their beliefs with the consistency of the beliefs. Typically, the correlation is 0. In one case where we have studied economists about their accuracy of beliefs about prostate cancer, early detection, and their consistency in terms of Bayesian consistency, the correlation was slightly negative. That is, there's no evidence that consistent Bayesians are more accurate than inconsistent Bayesians, which also you can understand that in the real world that doesn't matter very much. I mean, coherence.
How or why tallying does better than the weighting? Because I would have thought if people were assigning weights randomly, then in the long run, those two things would come out the same. So people must be doing something worse than assigning weights randomly. So what is it that they might be doing that could lead it to be worse?
So the question is, why can tallying, which assigns equal weights, be more accurate than multiple regression, who has the same variables but tries to estimate the beta weights from the sample that one has? So the reason is in situations where the variance, the error due to variance, or it's also often called overfitting, so the estimation error is larger than the bias that tallying has, assuming, so ignoring all the dependencies. If that holds, that's the bias variance dilemma, then you get this result. If, on the other hand, you are in a situation where, in out-of-sampling, where you have a large sample, and then at this point, the multiple regression could do better, and you can figure out this all with the same kind of logic. So, ignoring weights is also due to the study of ecological rationality. You find out, and basically you can just intuitively guess what the result is, namely, if in reality the weights are rather, similar to equal, then there's not much bias there. Or, and that's to the advantage of tallying because it avoids estimation error. Or if this is not the case, but you have a small sample size or an unstable world, then you do better by not guessing too much. That's the same problems as the one of the problems that caused the financial crisis. By all this guesswork with complicated estimation procedures like value at risk that estimates millions of parameters, and then you're lost.
Interesting. Okay. Thank you.
So there's a long-standing debate in the philosophy of science about the role of simplicity in theory choice, and because it seems that scientists prefer simpler theories, and yet it's quite hard to explain why they do. And I mean, one approach to that is very reminiscent of what you were saying about bias and variance. I mean, there's for example, Forster and Elliott Sober they've argued that the point of, or at least one rationale for preferring simpler theories is, well, in their terminology, is to avoid the problem of overfitting. That and they have very similar argument. That if you put some low bound on the order of the polynomial that you use, you will, you will get better predictions in the long run. So I might just wonder if you could comment about how close you think the connection is between the kind of thing you've been discussing and the apparent role of simplicity and theory choice in science.
Yeah. The connection is fairly close. So Forster is one of the authors of the first paper on fast and frugal trees, the Martineau papers. He has been in our research group. Elliott Sober has been connected. And what I'm doing here, I'm just providing a more theoretical foundation to all of that, to the talk about simplicity. Often people have realized since long that there is a problem of overfitting. But this analysis, the bias variance analysis, gives you the balance between overfitting and the bias, and a conceptual framework to understand when overfitting really causes damage, and therefore, when simpler models are likely to succeed. So yes, there is a clear, but it's also one of the very few philosophers I know who get interested in the role of simplicity. And if you know more, let me know.
Yeah, but well, I mean, sober certainly is, I would think, the issue. But I mean, I think it is recognized as a challenging issue, because on the one hand it seems to play such a crucial role in theory choice, and on the other hand it is difficult to, you know, initially to see why it's got any tendency to take us closer to the truth.
Yeah, but at the basis of this is the lack of understanding the difference between risk and uncertainty.
Yeah.
And most of the models, all the claims, they work very well about in the world of risk, like the entire Bayesian updating philosophy. And there is a Bayesian model called naive Bayes, which where one doesn't estimate the conditional probabilities, and which is very much in the spirit here, trying to reduce error through estimation. So that's variance, and simplify. And it's the experience is that this type of models, they can perform very well. And the question is, in what situation do they perform very well?
Yeah. I mean, just one comment. I mean, my own view is that this problem of overfitting is actually quite serious in epistemology itself, because there's a tendency for the methodology of a lot of discussion in epistemology to be largely driven by examples and verdicts on examples, and so people are looking for accounts that fit all the verdicts on the examples, and they're quite happy for these accounts to often to be very complicated accounts. And of course, if even one of the verdicts is on the cases is wrong, then they can, with this kind of complexity, which is as well the philosopher's equivalent of polynomials in a high degree. I mean, they can go off in completely the wrong direction.
Yeah. I'm glad that you are saying this and not me. And my wish would be, I have been with in my interdisciplinary work. Some people here have been in my group. We've always worked with philosophers, and I would just wish that philosophers are typically smarter than psychologists, but they are less curious, and they do not really want to know very much about the real world. And if I use your example, they create their own problem and overfit it, and think they have learned something. And it's a waste of talent. But you have your own internal reinforcement structure, career structure that supports that. So we need young philosophers who dare to think outside the box, and dare to save philosophy from this kind of isolationist, overfitting business.
And listening to your example for the simple model with few parameters, actually predicting better, I was reminded of a real-world scenario, different from a financial context, of stereotypes. And I'm just curious to hear your thoughts on this, and I was thinking that stereotypes can be seen as simple models with a few parameters, and they may be justified, that they balance, as I understand, bias and variance in a way that maybe makes prediction better. I wanted to say optimize, but I'm careful there. And actually, in conversations with other psychologists, I also have heard this argument used. Say, okay, it's natural for humans to have stereotypes because actually they predict better. yet also, though maybe not everybody would agree, but at least some people think it's normative to also battle stereotypes, because even though it may make prediction better, also people may suffer from them in various ways. Which again brings in sort of another idea. So, okay, so what are the costs? So you said like that there is no evidence that if you are not rational in classical sense that you incur costs, but then the question, what kinds of costs? So on the one hand, a majority may be able to predict well with stereotypes, but then minorities may incur costs, and how do you balance those? I'm just curious on your thoughts.
Yeah. This is an often and well-taken point that there seems to be a similarity between stereotypes and simple rules. But look, the stereotypes do have the structure, but they are not just caused by simple rules. If you look at big data and the experiences that Google or Facebook had with big data causing huge stereotypes at the end, you get the same out of there. So the psychology of stereotypes shows that you have to begin with something as a little child, and the point is that you are able to learn and revise them. That's the key point. So it is certainly true that without anything, so we should use the term stereotypes not in this negative version. So because there can be also positive stereotypes. And so one has to start with some bias and do some learning, and the bias variance dilemma is about a healthy balance between both of them that gets them. But in general, you find you can create stereotypes with any method, even with the most complicated deep learning neural networks.
Okay, thanks.
So in many of the decisions we make every day, not every day, in many of the decisions we make, the environment in which we are, it's very obscure. We don't know which cues we have to pay attention to. We don't have data before, and we don't even know our preferences. Say I want to buy a house. Okay, should I consider only the neighborhood? That's it, neighborhood. One property, that's it. Or should I have a more polynomial approach in which I have more aspects? Say, how large is the apartment? The neighborhood as well, whether there are schools or not, and whether it has a terrace. So the environment in which I'm going to make the decision is not a kind environment, as Robin would argue. It's an environment that is not helping me to be biased in any way. I have to consider more things. I have to go for a more complex model, even though I may end up confused. I may end up confused and may decide, yes, to buy an apartment because of the neighborhood, and that's it. But I don't have experience. I bought 2 houses in my life. I don't even know my tastes.
Yeah.
So I need to go for a complex model.
So I also bought 2 houses in my life, and that was when I bought my first house. I had less experience with the second one. I did it in half a day. And I had basically, that was in Chicago. This is a more, so many people probably do it like me. You have a certain, you consider an area. You have a consideration set first. You consider an area, a price level which you can afford, and a few others, mostly the size or so. And then I visited 3 houses, and I fell in love with the third one. That was it. And my wife operated on a different heuristic, because she was in Berlin at this time of point. No, in Göttingen. We were in Göttingen, yeah. And she just went with the heuristic, trust your husband.
Right.
And I phoned her, I have a house. Do you want to know more about it? She said, I trust you. So these are all heuristics. You may do it different, but I have not seen anyone calculating polynomials.
No, polynomials, it means that I give different weights to different properties. That's it.
Yeah.
And I calculate that, sorry. And you did, because you have more than one Q. Now, in the target that you put it, it was very, very clever done. So the bias was very close to the center of the target. while the variance was all around. But what about if I have a very strong bias that makes me throw the darts outside the target? Completely outside. So how do I know that my bias is going to be small or large if I don't have experience to contrast that?
So if you have no experience with a subject matter and need to make a choice, then people tend to rely on social heuristics, like my wife. So one is advice taking, another one is imitation. Imitate someone whom you believe knows something. So that's what many do when they go stock picking or so. So there's a number. My approach would be rather to look into what experts do, and even in your case, what someone does with no experience with something, and take that seriously and investigate it systematically. Imitation. The question is, in what situation is imitation likely to help you, and where is likely to fail you? That's the real question.
Exactly.
And there is a work by Boyd and Richardson a long time ago, and they say if the world is stable, then imitation is likely to succeed. Yeah, but if you inherit your business from your father, who was very successful in a time before globalization, then maybe imitating his strategy may not so likely to succeed. And that's the real question of ecological rationality.
I am wondering if the relationship between the bias and variance depends on how the data is treated before using it on a model. Because sometimes in the machine, at least in the machine learning algorithms, how the data is treated depends very much on how the beginning point will start, or near a local minima, or near the optimal solution. So I'm wondering.
Yeah. So this is correct. This is a situation where you cannot optimize, where you can, and so when we do this, the simulation results about take the best and the performance. If you run them, you don't run them once, but you run them maybe 10,000 times. And then you have a kind of safeguard against landing in a local minimum.
Last question for David.
You want to make some room for different kinds of cases. You're pushing the superiority of simple heuristics across the board. But when I'm in distress, I arrive in the emergency room at the hospital. I want the doctor to use some fast, quick strategy for just figuring out what needs to happen. But after that, I'm quite happy to spend weeks and lots of money and lots of tests to figure out what's really the best strategy. And in that case, we're using something that looks like it's approximating more to ideal rationality. So it seems to me that there's going to be different situations, some of which fit your model, but other ones don't fit so well.
Yeah, totally correct. Yeah, and there are situations in medicine where you have real good data and you can assume that the world is stable. Cancer screening is a good example. So mammography screening, there's data about 500,000 women, and there's no reason to assume that the world about mammography screening and breast cancer will change in the Western world in the near future. So in that situation, and if you, in fact, as you may know, I have the Harding Center of Risk Literacy, and we teach doctors to think the Bayesian way in this situation. And with natural frequencies and this kind of tools. This is part of my world. I'm talking today about situation of uncertainty, which is outside, and here, and that also already would emerge in this situation if there would be not just one test, like 1 mammograms, but 10 tests. With 10 tests, you would have to estimate the conditional probabilities in Bayes. Good luck. There's no data for that. And in that situation, fast and frugal tree, which would correspond to the Bayesian. It's much like take the best, but it does a classification. It can be investigated and shown that the more Qs you have, the more estimation error you get with Bayes, so do something simple. And the study of that is part needs to be done. So yes, we need, my opinion is, we need both statistical thinking in a world of risk, and we also need heuristic thinking in a world of uncertainty or intractability. And many situations have elements of both. And the heuristics here, they're not just coming from heaven, but they use the data, the little data available to do their best. And we need to take the distinction between risk and uncertainty seriously. And so last Wednesday I gave a talk. I'm on a lecture tour at the moment. a talk to the Swiss organization, medical organization for continuing medical education, mostly about risk, about understanding statistics, probability, Bayes rule, sensitivity, specificity, false positives, and so on, which doctors still don't learn. And 80% of the doctors are innumerate. Test your own doctor. And they don't know what a test means. So this is part also of my business to cover that field. But I also cover the other field of heuristics, and that's what I've been talking today about.